Hello student, welcome to my channel Learn Physics. Today I will be discussing a one-shot video on electric charge and fields. My topics are first of all introduction, then electric charge, conductors and insulators, charging by induction, basic properties of electric charge, Coulomb's law, forces between the multiple charges, electric field lines, electric flux, electric dipole in an uniform external field, continuous charge distribution, Gauss law, and application of Gauss law. I will be discussing on each topics with numericals on NCERT. So this video will be extremely helpful for 10+2, NEET, main and advanced. After watching this video, your concept become more and more clear. Okay, now let's start. Now charge. Charge is the fundamental property of matter by which it experiences electric and magnetic effect. Its properties are: number one, it is transferable. Okay. Number two, it is always associated with mass. Okay. Number three, a stationary charge particle produces electric field around it. Okay. No problem. Look at this. Now, a moving charge particle produces both electric and magnetic field, and an accelerated charge particle not only produces electric and magnetic field, it radiates electromagnetic wave. Okay. Next, number 4, quantization of charge. The charge in a body is always integral multiples of electronic charge. Suppose Q be the magnitude of a charge, then Q equal to N into E, where E is the magnitude of electronic charge, that is 1.6 into 10 to the power minus 19 coulomb. Okay. Number 5, the additive nature of charge. The charge in a body is sum of the charges in it. Suppose Q1, Q2, Q3 be the charges in a body, then total charge in the body is Q1 plus Q2 plus Q3. Okay, understood? And finally, conservation of charge. The charge in a system is always constant. Suppose, look at this, an electron, this is the -1, 0, and a positron forms gamma particle. So this is the gamma. Look at this, before combination, the total charge -1 plus 1 equal to 0, and after combination the charge is also 0. Okay. Now a related numerical on NCERT. Now a numerical relating to this. If 10 to the power 9 electrons move out of a body to another body every second, how much time is required to get the total charge of 1 coulomb on the other body? Okay. Now look at this, the number of electron transfer, this is equal to 10 to the power 9 electron per second. So charge in it, this is the 10 to the power 19 into 1.6 into 10 to the power minus 19 per second. So look at this. This is the 1.6 into 10 to the power minus 10 per second. So look at this, 1.6 into 10 to the power minus 10 coulomb charge is transferred from one body to another body. So time required to get the charge of 1 coulomb, this is the total charge 1 coulomb divided by number of charge transferred in 1 second. So look at this, this is the 1 by 1.6 into 10 to the power minus 10 second. So look at this, this is the 10 to the power 10 by 1.6. So look at this is the 6.25 into 10 to the power 9 second is the answer. Okay, next. Now look at this another numerical. How much positive and negative charge is there in a 1 cup of water? Suppose 1 cup of water, this is the 250 gram of water. Okay, look at this. The amount of water, this is the 250 gram. So number of mole, so number of mole, this is the 250 divided by 180. Okay. Now number of molecule, this equal to this into Avogadro number. Number of molecule, this is the 250 by 18 into Avogadro number 6.023 into 10 to the power, this is the 23. Now this and this is the 3 almost. Now one molecule of water contains, this is the 8 electron in oxygen atom and 1 electron in hydrogen atom. So there are 2 hydrogen atom. So total number of electron in one molecule of water, this is the 10 electron. So look at this negative charge. So negative charge, this is equal to, this is the 250 by 3 into 10 to the power 23 into charge into 10 into charge of electron 1.6 into 10 to the power minus 19. This is the negative side. Okay. Now look at this. This is the 10 to the power 23 and 10 to the power minus 19. So look at this. This is the 10 to the power 4. No problem. Now look at this. 10 into 1.6, 16. Now 16 into 250. So look at this. This is the 4000. Okay. 4000 divided by 3. So look at this, this is the 1.33 negative side into 10 to the power, this is the 7 coulomb charge. So look, this is the negative charge and equal amount of positive charge also present. Okay, next. Now conductors. The substance which conduct electricity are called conductors. Okay, like aluminum, copper, silver, etc. Okay. Now insulator. The substances which does not conduct electricity are called insulator, like air, wood, etc. Okay. If the electric field in air medium is 3 into 10 to the power 6 volt per meter, then air becomes conductor. That means if a potential difference of, this is the 30 kilovolt is applied between the 2 points separated by the distance of 1 centimeter, then air between this space becomes conductor. So actually insulators are not insulator, they are conditional insulator. During lightning, the large amount of charge of cloud comes to the earth through the air medium because of dielectric breakdown of air medium. Okay. Now charging by rubbing. When two different substances are rubbed with each other, electron of one substance transferred to the other substance. So one substance has a deficit of electron and other has surplus of electron. Okay. The substance which has deficit of electron gets positive charge and the substance which has surplus of electrons gets negative charge. If n number of electrons transferred from this body to this body. So charge in this body is this is the n into 1.6 into 10 to the power minus 19 coulomb, and charge in this body this is the minus n into 1.6 into 10 to the power minus 19 coulomb. What is the change of mass? As electron has mass, so the body which has surplus of electrons is heavier than the body which has a deficit of electron. The change of mass, this is the delta M, this equals to n into 9.1 into 10 to the power minus 31 kg. Okay, no problem. So this body has less mass by this, and this body has surplus of mass by this. Okay, no problem. Next. Now look at this NCERT numerical 1.11. A polythene piece wrapped with a wool is found to have a negative charge of 3 into 10 to the power minus 17 coulomb. Okay, estimate the number of electron transferred. Look at this. We know the number of electron transfer n equal to q by charge of electron. Now look at this. This is the charge is equal to 3 into 10 to the power minus 7. So look at this. This is the 3 into 10 to the power minus 7. Okay. Now look at this. This is the electronic charge 1.6 into 10 to the power. This is the minus 19 coulomb. So look at this. This is the 3 by 1.6 into this is the 10 to the power 12. This is almost equal to 2 into 10 to the power 12 electron transferred from wool to polythene. Okay. Now, second question, is there any transfer of mass from wool to polythene? Yes. Look at this. The increase of mass of polythene delta M, this equals to 2 into this is the 10 to the power 12 into mass of 1 electron. This is the 9.1 into 10 to the power minus 31 kg. Okay. So look at this. This is the almost 18 into 10 to the power. This is the minus 19 kg. So increase of mass of polythene is this, and decrease of mass of wool is this. Okay, no problem. Next. Now charging by conduction. Okay, look at this. Suppose this is a charge body. Okay, it is charge q. If this body is in contact with another body with the help of metallic wire, now the charge is shared by this uncharged body. If these two bodies are identical, then charge of each body, this is the q by 2 and q by 2. Okay. If this body has charge q1 and this body has charge q2, then after sharing the charge on each body, this is the q1 plus q2 by 2. Okay. Now charging by induction. Now first of all, what is induction? If a charged body is brought near an uncharged body, then the uncharged body gets charged. This phenomenon is known as electrostatic induction. Now look at this. Suppose this is a charged body. Suppose it has positive charge. No problem. Okay. If an uncharged body is brought near it, now the near end of this body gets negative charge. Okay, and far end gets positive charge. This is known as induced bound charge, and this is known as induced free charge, and this is the inducing charge. The magnitude of inducing charge is equal to magnitude of induced bound charge is equal to magnitude of induced free charge. Now, if this body is earthed, then positive charge is neutralized by the electron from the earth. Okay. Now, induction precedes attraction. Look at this. When an uncharged body is brought near a charged body, at the near end of uncharged body gets unlike charge and far end gets like charge. the force of attraction between two unlike charges, force of attraction between two unlike charges is more than force of repulsion between the like charge. That is why that is why an uncharged body is attracted towards the charged body. So induction precedes attraction. Okay. Now can you get positive and negative charge with the help of induction? Okay. Now how can you get positive and negative? Now how can you get the positive and negative charge with the help of induction? Look at this. Now look at this. This is the positive charge. Okay. Now, this is an uncharged body. Now, this is another uncharged body. They are in contact. Now, this is an insulating handle. Now, look at this. This is also an insulating handle. No problem. Look at this. Due to induction, this body gets negative charge. No problem. And this body gets positive charge. Now, keeping the inducing charge here, the two bodies are separated from each other. So look at this. Now look at this. This body. Now one body gets positive charge. Okay, no problem. And other body. Look at this. And other body gets negative charge. Okay. So in this way, we can get positive and negative charge simultaneously with the help of induction. Okay, you too. Now look at this, a numerical on electrostatic induction. Now Ncert numerical 1.28. A conductor A has a cavity shown in figure. Look at this. This is the conductor A. Okay. Look at this. A conductor A with cavity as shown in figure is given a charge Q. Look at this Q charge given on it. As it is conductor, this Q charge always remain outside the surface. Okay. So charge always resides outside the surface of a conducting body. Okay. No problem. There is no charge inside it. Okay. Now look at this B. Another conductor B with a charge Q is inserted into the cavity, keeping B inserted from A. Look at this. Look at this here. Q charge positive is inserted within the cavity. So due to electrostatic induction, here negative charge induced. So inner surface of the cavity gets minus Q charge. And outer surface, look at this, outer surface gets, look at this, this is the Q charge, small Q charge due to induction. As the body already has charge plus Q, so total charge in it, this is the capital Q plus small q. Okay, no problem. Now question C. A sensitive instrument is to be shielded from the strong electrostatic field in its environment suggests the possible way. Look at this here, no charge present within the cavity. If a sensitive instrument kept in a metallic box, then field within the metallic box remains zero. So a sensitive instrument can be shielded from the electrostatic field by keeping it within the metallic box. Okay, next look at this. Suppose Q1 charges and Q2 charges are separated by the distance r. Okay, r is the distance of separation. The Coulomb's law of electrostatic interaction is acting along the line joining the two charges. Look at this. This is the Q1 and Q2 are the two charges. So this force acting along the line joining the two charges. The force on Q2 by Q1, this is the F21. And force on Q1 by Q2, this is the F12. These two forces are acting along the line joining the two charges. and magnitude of these two forces are equal and opposite in direction. Okay, understood? The magnitude of force of interaction is directly proportional to magnitude product of magnitude of two charges and inversely proportional to square of distance of separation, and this force also depends on medium. Okay, no problem. Therefore, combining this relation, we get F equal to, this is the 1 by 4 pi epsilon into Q1 Q2 by R square, where epsilon is the permittivity of the medium, where 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 epsilon is the permittivity of the medium. Now look at this. This can be written as, this is the 1 by 4 pi epsilon naught into K into Q1 Q2 by R square. No problem. Where K is called dielectric constant and this equal to epsilon by epsilon naught. So dielectric constant of a medium is the ratio between permittivity of the medium and permittivity of the free space. Okay, so it has no unit. Now the value of epsilon naught, this is the 8.85 into 10 to the power minus 12, this is the Coulomb square Newton inverse meter to the power minus 2, or it can be written as 9 into 10 to the power minus 12 Newton meter in Coulomb square Newton inverse meter to the power minus 2. Okay, and the value of, look at this, 1 by 4 pi epsilon naught, this equals to 9 into 10 to the power 9, this is the Newton meter square by Coulomb square. Okay, so look at this, from this relation we can get, this is the 1 by K into F naught, where F naught is the force of interaction between the two charged particle Q1 and Q2 in air medium or free space. So look at this, force of interaction in a medium F equal to force of interaction between the same two charges in air divided by K. For K for air, this is the 1, K for free space is also 1, K for water, this is the 80, and K for metal, this is the infinity. Okay, understood? Now look at this, the now look at this, the vector representation of Coulomb's law. The force on Q2 by Q1, this is the F21 vector, this is the, look at this, Q1 Q2 by, this is the 4 pi epsilon naught into R square, this is in air medium, and the unit vector directed from, look at this is the, look at this is the R12 cap, where R12 cap is the unit vector directed from Q1 to Q2. Okay, in the same way, look at this force on, look at this, the force on F12, force on Q1 by Q2, this is the Q1 Q2 by 4 pi epsilon naught R square, this is the R cap to 1. So look at this, as this and this are equal and opposite, so F12, so F1 vector equal to F12 vector. Okay, now some numerical based on Coulomb's law. Okay, now look at this question number 1.1. What is the force between two small charge sphere having charges 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed 30 centimeter apart in air? Now look at this, you know F equal to, this is the Q1 Q2 divided by 4 pi epsilon naught R square. Look at this here, Q1 equal to, this is the 2 into 10 to the power minus 7. Q2 equals to 3 into 10 to the power minus 7. Okay. Now 1 by 4 pi epsilon naught, this equals to 9 into 10 to the power 9 Newton meter square divided by Coulomb square. And look at this, R equals to, this is the 30 centimeter, so this is the 0.3 meter. So look at this, F equal to, this is the 9 into 10 to the power 9. Look at this value of 1 by 4 pi epsilon. Now Q1, this is the 2 into 10 to the power minus 7. Q2, this is the 3 into 10 to the power minus 7, divided by 0.3 whole square. Okay, so look at this, this is the 9 into 10 to the power, this is the 9 into 6 into 10 to the power minus 14, divided by, look at this is the 9 into 10 to the power minus 2. So look at this and this cancel out. Okay, now look at this and this. Now 10 to the power 9 and 10 to the power minus 14. So look at this is the 10 to the power minus 5 into 6 divided by 10 to the power minus 2. So look at this, 6 into 10 to the power minus 3, 10 to the power minus, so 6 into 10 to the power minus 3 Newton is the force of interaction between the two charge particles. Okay, next. Now, question number 1.2. Electrostatic force on a small sphere of charge. This is the Q1 equal to 0.4 microcoulomb. Now, 1 microcoulomb equal to 10 to the power minus 6 coulomb. Okay. Due to another small sphere having charges, look at this, 0.8 microcoulomb. So Q2 equal to, look at this negative sign of, this is the 0.8 into 10 to the power minus 6 coulomb. Okay, in air is 0.2 Newton. Look at this, F is given, F is the 0.2 Newton. What is the distance between the two charges? Now you also know 1 by 4 pi epsilon naught, this equals to 9 into 10 to the power 9. We have to calculate R, distance between the two charges. No problem. Now look at this. Now look at this here, F equal to, this is the 1 by 4 pi epsilon naught into Q1 Q2 by R square. Look at this, F is the 0.2 Newton. Okay. Now look at this is the 9 into 10 to the power 9. Q1, what is Q1? Q1 is the 4.4 into 10 to the power minus 6. Q2, this is the 0.8 into 10 to the power minus 6 divided by a distance square. So look at this, R square equal to, look at this is the 10 to the power minus 6, 10 to the power minus 6. That is the 10 to the power minus 12 into 10 to the power 10. So look at this is the 10 to the power minus 3. So this is the 9 into, this is the 0.32 into 10 to the power minus 3 whole divided by, look at this is the 0.2. So look at this here, this is the 9 into, this is the 0.16 into 10 to the power minus 4. So look at this, R equal to, this is the 3 into 0.4 into 10 to the power minus 2. So look at this is the 1.2 into 10 to the power minus 2 is the distance between the two charge particles. So distance between the two charge particles R equals to 1.2 into 10 to the power minus 2 meter. Okay, what is the force on the second sphere due to the first? You know the Coulomb's force of interaction is the mutual force of interaction. So force on first by second is equal to force on second by first, but in opposite direction. Okay. Now look at this 1.3. Check the ratio of K E square divided by G ME MP is dimensionless. Now look at this. This is the K E square divided by G. This is the ME MP. Okay. Look at this, K E square by R square whole divided by, look at this, G ME MP divided by R square. Look at this is the electrostatic force of interaction between proton and electron. Look at this. This is the Fe, and this is the gravitational force of interaction between proton and electron. So look at this. These are the two forces. So it is a dimensionless. Okay. Look up a table of physical constant and determine the value of this ratio. Now look at this. The value of this ratio. Look at this. This is the K is the 9 into 10 to the power 9. E is the 1.6 into 10 to the power minus 19 whole square. Divide by, look at this. This is the 6.67 into 10 to the power minus 11. Mass of electron, this is the 9.1 into 10 to the power minus 31 kg, and mass of proton 1.67 into 10 to the power, this is the minus 27. Okay. By calculating this ratio, we get, look at this, this is the 2.4 into 10 to the power 39. So look at this large ratio signifies that the electrostatic force of interaction between proton and electron is much greater than the gravitational interaction between the two particles. Okay. So gravitational force is negligible in comparison to the electrostatic force of interaction. Okay. Now definition of unit charge. Okay. The Coulomb's law between two charged particles in air medium, this is the 9 into 10 to the power 9 into Q1 Q2 by R square. If Q1 equal to Q2 equal to Q, R equal to 1 meter, and F equal to, this is the 9 into 10 to the power 9 Newton, then from this relation we get, look at this, this is the 9 into 10 to the power 9, this also 9 into 10 to the power 9, and this is the q square by 1 square. So look at this, q square equal to 1, therefore q equal to plus minus 1. Therefore, if two identical charged particles are separated by a distance of 1 meter in air medium and experiences a three repulsive force of 9 into 10 to the power 9 Newton, then magnitude of each charge is called unit charge. In SI system, it is known as coulomb. 1 coulomb, this equal to 3 into 10 to the power 9 ESU. Okay. Now superposition principle. Suppose, look at this, this is a square. Okay. Now charge Q1, charge Q2, charge Q3 and charge Q4 are placed at the vertices of square. Okay. Now we have to calculate the force on Q2 by Q1, Q4 and Q3. Okay. No problem. Now look at this. The force on Q2 due to, look at this, the force on Q2 due to Q1 is directed along this direction. The force on Q2 due to Q3 is directed along this direction. Okay. And force on Q2 due to Q4 is directed, look at this, is directed along this direction. Okay. Now this force on Q2 by Q1, this is the F21. This force on Q2 by Q4, so this is the F24, and this force on Q2 by Q3, so this is the F23. The net force on Q2 is the vector sum of this force and this force. Okay. Now a numerical relating to this. Okay. 4-point charges QA equal to 2 microcoulomb, QB equal to, this is the minus 5 microcoulomb, QC is the 2 microcoulomb and QD is the minus 5 microcoulomb are located at the corners of a square ABCD of side 10 cm. What is the force on charge 1 microcoulomb placed at the center of the square? Okay. Now look at this. This is the square. Okay, no problem. Look at this. Look at this. This is the point A. This is the point B. This is the point C. This is the point D. Okay. Now the charge on A is QA. So QA is this is the 2 microcoulomb. Now QB, this is the minus 5 microcoulomb. QC, this is the 2 microcoulomb. And look at this is the D, this is the minus 5 microcoulomb. Okay. Now a charge placed at the center, this is the 1 microcoulomb, and side of the square is the 10 centimeter. Okay. Now look at this, we have to calculate the electrostatic force on 1 microcoulomb placed at the center. Okay. Look at this, the force on 1 microcoulomb by 2 charge is same as force by 2 microcoulomb on this charge. Okay, no problem. So look at this, these two forces are cancel one another. Okay, suppose this is the O. So look at this force is the FAO. Now look at this force is the FOC. In the same way, look at this, the force on O by 5 microcoulomb is directed on this direction. So look at this force, this is the 5 OD. And look at the force on 1 microcoulomb by 5 microcoulomb, this is the 5 OB, are directed on this direction. Now look at this force and this force cancel out, this force and this force cancel out, so net force acting on it is 0. Okay. Now look at this numerical 1.1. Two insulated charged copper sphere A and B have their centers separated by a distance of 50 centimeter. What is the mutual force of electrostatic repulsion if the charge of each is 6.5 into 10 to the power minus 7 coulomb, and radii of A and B are negligible in compared to the distance of separation? Now, first of all, what is the distance of separation? Distance of separation, this is the 50 centimeter. So look at this. We have to calculate the interaction. Now we have to calculate the force of interaction. Look at this. The force of interaction F equals to, this is the 9 into 10 to the power 9. Now this is the Q1 and Q2. So look at this. This is the 6.5 into 10 to the power minus 7 into 6.5 into 10 to the power minus 7 divided by, look at this is the 0.5 whole square. So look at this is the 0.5 whole square means 1 by 4. So look at this is the 4 into 9 into 6.5 whole square into, look at this, 10 to the power, this is the minus 5, because 10 to the power minus 7, 10 to the power minus 7 and 10 to the power 9. So this is the 10 to the power minus 5. No problem. Okay. So look at this is the 36 into, this is the 6.5 whole square. This is the 1521 into 10 to the power minus 5. So look at this is the 0.015 Newton is the force of interaction between the two charged particles. Okay. Now look at this. What is the force of repulsion of each sphere is charged double the above amount? If the charge of each sphere double, then force becomes 2 into 2, that is the 4 times. And look at this, the distance between them is half. Now distance between them half, so force also becomes 4 times. So the net force becomes 16 times of initial amount. Okay. So look at this is the 0.24 Newton is the force of interaction if the charges are double and distance of separation becomes half. Okay. Now electric intensity. First of all, definition. Electric intensity is the force per unit charge acting on a vanishingly small test charge. Look at this, electric intensity is equal to limit, this is the Q naught tends to 0 F by Q naught. So its unit becomes Newton per coulomb or volt per meter, and dimension, look at this is the mlt minus 2 by at, so its dimension is mlt minus 3 a minus 1. Okay, no problem. Next, suppose this is the charge q. Look at this here, charge q naught. Now force on q naught by q, this equal to 1 by 4 pi epsilon naught, this is the q naught by r square. So electric intensity E equal to, look at this is the limit q naught tends to 0, f by q naught, this is the f. Okay, so this is the f by q naught, so this becomes q divided by 4 pi epsilon naught r square. That is, we can retain as this is the kq by r square. No problem. Look at this, look at this, due to positive charge, the electric intensity E is directed away from the charge. And look at this, due to negative charge, this point, the electric intensity is directed towards the charge. Okay, no problem. Now a numerical. Suppose this is the charge q. This is the charge q. Okay, the distance of separation between the two charges, look at this is the 2r. We have to calculate the intensity at the midpoint P. So look at this, due to positive charge, it is directed along this direction, and magnitude E equal to, this is the kq by r square, and due to this charge, look at this, the intensity is directed, this is the E dash, this is the kq by r square. Look at this intensity and this intensity are equal and opposite, so net intensity at this is equal to 0. Now look at this, another example. Look at this, here charge q and here charge minus q. Separation is same 2r. Okay. Now we have to calculate intensity at the midpoint. Okay. Now due to positive charge, electric field directed away from it, and due to negative charge, electric field at this point is directed towards the charge. So look at this, net electric field becomes, this is the 2kq by r square. Okay. No problem. Now, a numerical related to electric intensity. Now, a numerical 1.8 due to electrostatic field. Look at these 2-point charge, QA equal to 3 microcoulomb, QB equal to minus 3 coulomb are located at 20 centimeter apart in vacuum. What is the electric field at the midpoint O of the line AB joining the two charges? Okay, this is the very simple. Look at this. This is the charge QA. Now QA equal to, this is the 3 microcoulomb, and look at this is the QB, this is minus 3 microcoulomb. Okay, now we have to calculate the intensity at the midpoint. You know, due to positive charge, intensity directed along this direction, due to negative charge, intensity directed along this direction, so net intensity directed towards the negative charge, and this equals to, this is the 2kq by r square. Now look at this is the 2, k is the 9 into 10 to the power 9, q is the 3 into 10 to the power minus 6, and r, look at this, the total distance, this is the, now total distance, this is, now the total distance is the 20 centimeter, so half distance is the 10 centimeter, so this is the 0.1 whole square. Okay, so look at this is the 54 into 10 to the power, this is the 5 Newton per coulomb. Okay, now question number B. Charge, if a negative test charge of magnitude 1.5 into 10 to the power minus 9 coulomb placed at this point, what is the force experienced by the test charge? Now force experienced by test charge, look at this is the 1.5 into 10 to the power minus 9 into E, and it is directed in the direction of the field. Okay, so look at this is the 1.5 into 10 to the power minus 9 into, look at this is the 54 into 10 to the power 5. So look at this, this is the 5.4 into 10 to the power 6. Therefore, look at this, 1.5 into 5.4. So look at this, this is the 8.1 into 10 to the power minus 3 Newton is the force experienced by this charge. Okay, no problem. Now, force on a charge particle in electric field. Okay, look at this. Suppose an electric field is directed along this direction. Okay, if a charge particle Q is placed here, so force acting on it, this is the Q into E. If this is the vector, this also the vector. That is a positive charge directed along the direction of the field and a negative charge directed opposite to the direction of the field. So acceleration of the charge particle, look at this, action of the charge particle, this is the force by mass. So look at this, this is the QE by M. Now velocity of the charge particle in the direction of the field, V equals to 0 plus AT. So look at this, velocity becomes QE T by M after the time T. Now Ke of the charge particle, Ke equal to, this is the half mv square. So look at this, this is the half m, v is the, this is the q square, e square, t square by m square. Okay, so look at this is the q square, e square, t square by 2m. Okay, no problem. Now displacement y equal to, this is the half QE by m into t square is the displacement. Okay. Now a numerical related to this. Now question number 1.25. An oil drop of 12 axis electron is held stationary under a constant electric field 2.55 into 10 to the power 4 Newton per Coulomb. Millikan's oil drop experiment. The density of the oil is 1.26 gram per cc. Estimate the radius of the drop. Okay, this is the oil drop and it has 12 excess electron. No problem. Now the forces acting on this oil drop due to its weight, this is the mg, and this is the directed vertically downward, and this equal to, this is the 4/3 pi r cube rho into g. And look at this is the electrostatic force. Look at this is the QE. Here electric field obviously directed in the downward direction because it is the negative charge experience force opposite to the direction of field. Okay, no problem. So look at this, as it is equilibrium, electrostatic force is equal to gravitational force. Now look at this, so this is the 4/3 pi r cube, this is the r cube rho. Look at this, density is the 1.26 gram per cc. So in SI system it becomes 1260, and G is the, look at this is the 9.81. This equal to, this is the Q into E. Look at this, Q is the 12 axis electron. So this is the 12 into 1.6 into 10 to the power minus 19 Coulomb. And electric field, this is the 2.55 into 10 to the power 4. Okay, no problem. Look at this here, RQ equal to, this is the 2.55 into 12 into 1.6. So look at this, 2.55 into 12 into 1.6 into 10 to the power, this is the minus 15, whole divide by, look at this is the 4 pi into 1260 into 9.81, and this is the 3. Okay, so look at this is the RQ equal to, this is the 9 point, so this is the 9.46. So look at this is the 9.46 into 10 to the power minus 12. So R equals to, look at this is the third root of 9.46 into 10 to the power minus 4. Okay. So look at this is the 2 into 10 to the power minus 4 meter is the radius of the drop. That is, this is the 0.2 millimeter is the radius of the drop. Okay. Now look at this question number 1.33. A particle of mass m, charge minus q, enters a region between the two charge plates initially moving along x-axis with velocity vx. Okay, the length of the plate is L, and an uniform electric field is maintained between the two plates, so that the vertical deflection of the particle at the far edge of the plate is QEL square divided by 2m Vx square. Now look at this. Look at this. This is the two parallel plates. Okay, this is the x-axis. Now this is the x-axis. A charged particle moves with velocity Vx along this direction, and here electric field is directed along this direction. So axis of the charged particle along this direction A equal to, this is the QE by M. Now after the distance Lx, the deflection of the charged particle is y. So look at this time taken by the charged particle to cover the distance L. This is the L by Vx. So y equal to, this is the half a t square. Now look at this. This is the half a. A is the, this is the QE by M, and a and t is the L by Vx whole square. So look at this. This is the y equal to QE L square divided by 2m Vx square. Okay. It's a numerical. Now a same type numerical here. Suppose that the particle in exercise 1.33 is electron. So look at this. Q is equal to 1.6 into 10 to the power minus 19 coulomb. Okay. Projected with velocity Vx equals to 2 into 10 to the power. So look, projected with velocity Vx equals 2 into 10 to the power 6 meter per second. Look at this. Vx equals to 2 into 10 to the power 6 meter per second. E between the two plates separated by 0.5 centimeter is 9.1 in 10 to the power 2 Newton per coulomb. So look at this. Here y equal to, look at this. This is the 0.5 centimeter. So this is the 0.5 into 10 to the power minus 2. And look at this. Here electric field E equal to, look at this. This is the 9.1 into 10 to the power 2 Newton per coulomb. Okay. Where the electron strikes the upper plate, we have to calculate L. Okay. Now look at this. The relation is, look at this. So look at this from here. L square equal to, this is the 2m Vx square into y divided by u into E. Okay. Put this value. Look at this. This is the 2 into, this is the 9.1 into 10 to the power minus 31 kg. Now Vx, look at this. Vx is the 2 into 10 to the power 6. So Vx square, so this is the 4 into 10 to the power 12. Okay. Now y, look at this. Y equals to 0.5 into 10 to the power minus 2. So look at this. This is the 0.5 into 10 to the power minus 2. Whole divided by, this is the Q into E. Q is the electron. So look at this. This is the 1.6 into 10 to the power minus 19 coulomb. E is the 9.1 into 10 to the power 2 Newton per coulomb. Now look at this. Now look at this. This and this cancel out. Look at this. This is the 4 into 2 into 0.5. So look at this. This is the 4. Now 10 to the power minus 3. Now 10 to the power minus 31 into 10 to the power 12. So 10 to the power minus 19. 10 to the power minus 19 into 10 to the power minus 2. So 10 to the power minus 21. 10 to the power minus 21 and 10 to the power 19. So 10 to the power minus 2. Now 10 to the power minus 2 into 10 to the power 2. So look at this. This is the 10 to the power minus 4. No problem. And look at this. This is the 1.6. So look at this. This is the 2.5 into 10 to the power. This is the minus 4. So So look at this. This is the L equal to, this is the 1.6 into 10 to the power minus 2 meter. Therefore, L equals to 1.6 centimeter. Okay, understood? Next. Now, electric dipole. Suppose two charges minus Q and Q separated by a distance d, then they constitute an electric dipole. Okay, the dipole becomes ideal if magnitude of charge is very large and distance of separation is very small. Now, dipole moment. The dipole moment P is the product of magnitude of a charge and their distance of separation between the two charge is called dipole moment. So dipole moment is the Q into D. It is a vector quantity directed from negative charge to positive charge. Okay, and its unit, obviously this is the coulomb meter and dimension A T L. Okay, now force on a dipole in an uniform electric field E. Okay, suppose a dipole, look at this, suppose a dipole is placed here. Okay, look at this, this is the positive charge and this is the negative charge. Okay, so a force experienced by the positive charge is QE along this direction and force experienced by minus Q charge is along this direction. This is the minus QE. So in uniform electric field, the net force on the dipole, look at this, this is the QE minus QE equal to 0. So force acting on uniform electric field is 0. So there is no translational motion of a dipole in uniform electric field. But in non-uniform electric field, this force is non-zero. Therefore, a dipole experiences a translational motion in non-uniform electric field. Okay. Now the forces QE and minus QE are equal, opposite and parallel. So they constitute a couple. The moment of the couple, look at this is the tau is equal to the magnitude of force into their distance of separation. If d be the distance between the q and minus q and angle be the theta, then look at this distance between the two forces, this is the d sine theta. Therefore, torque tau equal to QE into d sine theta. Now, you know d into q, that is the dipole moment P into E into sine theta. Okay, so tau equal to P sine theta. Therefore, tau vector, this is the P vector cross E vector. Okay, no problem. Therefore, in uniform electric field, a dipole experiences a torque but no force. But in non-uniform electric field, a dipole experiences both force and torque. Okay. Now look at this question number 1.10. An electric dipole with dipole moment 4 into 10 to the power minus 9 coulomb is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 to the power 4 Newton per coulomb. Calculate the magnitude of torque on the torque acting on the dipole. You know the magnitude of torque acting on the dipole tau equal to, this is the P E sin theta. Now look at this, theta is 30 degree, this is the P, okay, and this is the E. Now put the value of P, this is the P, this is the E and this is the theta. So look at this, P is the 4 into 10 to the power minus 9. E is the 5 into 10 to the power 4 and this is the sine 30 degree. Therefore, look at this is the 20 into 10 to the power minus 5 into half. So look at this, 10 to the power minus 4 Newton meter is the force acting on the dipole. Okay. Now, potential energy in a uniform electric field of a dipole. Look at this, the torque experienced by a dipole when it makes an angle theta with the electric field, this is the P sin theta. Okay. Now, amount of work done to turn the dipole from theta to theta plus d theta, this equal to tau into d theta. That is, this is the Pe sin theta d theta. Therefore potential energy U equal to, this is the integration of, this is the tau d theta from 90 degree to theta. So look at this is the Pe sin theta d theta integration of, this is the 90 degree to theta. So look at this is the Pe, this is the minus cos theta. Therefore potential energy, this is the Pe cos theta with negative sign. Therefore U equal to minus P vector dot E vector. Okay. Now, amount of work done to turn the dipole delta W equal to, look at this is the U2 minus U1. Now, U2 minus U1, that is, this is the minus Pe cos theta 2 minus, this is the Pe cos theta 1. Therefore, Pe into cos theta 1 minus cos theta 2. Okay, no problem. This is the work done. Look at this. Suppose a dipole minus Q and Q is placed here. Okay. This is the point A and this is the point B. Center of the dipole is O. And the dipole moment P equal to, this is the Q into D is the dipole moment. Okay. Now we have to calculate the intensity at the axis of the dipole at a distance smaller from the center of the dipole. That is here OP equal to R. If OP equal to R, then what is the AP? Look at this, AP equal to R minus, this is the OA, that is D by. And what is the BP? BP equals to R plus, this is the D by. Now look at this electric field due to Q charge at this point. Look at this, directed along this direction E1, and electric field due to negative charge and electric field at the point P due to minus Q charge, this is the E2 is directed towards the dipole. Now what is E1? E1 is the, look at this is the KQ by distance square. Distance square means AP square. AP is the R minus D by 2 whole square. Okay. What is E2? E2 is the, look at this, KQ divided by distance square. What is the distance? Distance is the R plus D by 2 third whole square. R plus D by 2 third whole square. Look at this, E1 directed away from the dipole, E2 towards the dipole. So net electric field, this is the E1 minus E2. So look at this is the KQ into, this is the 1 by R minus D by 2 third whole square minus 1 by R plus D by 2 third whole square. Okay, no problem. So look at this is the K into Q. Look at this is the R square minus D square by 4. This is the 4R D by 2. Okay. Look at this. This is the K into Q into D. QD is the P and this is the 2R. And if D is very, very small in comparison to R, so look at this. This is the R to the power 4. So look at this electric field E equal to, this is the 2 Kp by RQ. Okay, and look at this P vector directed along this direction, electric field vector also directed along this direction. So E vector is equal to dipole moment vector. Okay, now we have to calculate the electric field on the perpendicular bisector position. Okay, now look at this. This is the perpendicular bisector position. Okay, now this is the minus Q and this is the Q. This is the O Okay, this is the point A, this is the point B. We have to calculate the electric intensity on the perpendicular bisector position at P, where OP equal to this is the R. Okay, no problem. Now look at this. A line is drawn. Now line AP is drawn. The electric field due to positive charge is directed along this direction. Look at this. This is the electric field due to Q charge, and suppose this is the E1. Okay. Now look at this. The electric field due to minus Q charge. Look at this. A line is drawn from minus Q to P. Okay. Now electric field due to minus Q charge is directed along this direction. Suppose this is the E2. Okay. Now look at this. The AB is the D and this is the R. So look at this here. AP equal to BP equal to root under of, look at this is the R square plus D square by 4. Okay. Now look at this, the electric field at P due to Q charge, this is the E1, this equals to, this is the Q divided by KQ divided by, this is the AP square, and directed away from positive charge. Now E2 equal to, this is the KQ divided by BP square and directed towards negative charge. Okay. Now look at this. A line is drawn parallel to dipole moment vector. And this dipole moment vector, now a line is drawn opposite to the direction of dipole moment vector. Look at this. If this angle theta, then this angle also theta. So this angle theta and this angle theta. The component of E1 along this direction, this is the E1 cos theta. And component of E2 along this direction, this is the E2 cos theta. Now the other component, look at this is the E2 sin theta is cancelled by the component E1 sin theta. Okay, no problem. Therefore, the resultant electric field E equal to, on the perpendicular, the resultant electric field on the perpendicular bisector position is directed along this direction opposite to the direction of dipole moment P vector. So E equal to, look at this is the 2 KQ divided by AP square or BP square. What is the AP square? AP square is the R square plus D square by 4. And cos theta, look at this, cos theta equal to D by 2 divided by root under of, this is the R square plus D square by 4. Now this and these two are cancelled out. So look at this is the K into Q into D whole divided by, this is the R square plus D square by 4 to the power 3 by 2. This is the electric field E. Okay. Now look at this. This is the K into P whole divided by R cube is D very small in comparison to R. Therefore, E vector is equal to negative sign of K P vector by R cube. So look at this. The electric field on the perpendicular bisector position is half of electric field on the axial position if distance is same, and electric field on the axial position is directed along the direction of the P vector, and in perpendicular bisector position is directed away from the P vector. Okay, no problem. Now look at this continuous charge distribution, linear conductor. Here this is the charge linear conductor. The charge per unit length of a conductor is called linear density of charge. Its unit is coulomb per meter. Okay. Now look at this. This is surface having charge delta Q in the area delta S. So surface density of charge sigma equals to, this is the delta Q by delta S. Now for a conducting sphere, look at this is the conducting sphere or spherical shells, charge reside over the surface If r be the radius of the conducting sphere or spherical shell, then look at this. Here sigma becomes u divided by area, that is 4 pi r square. Its unit is coulomb per meter square. Now, for an insulating sphere, look at this. For insulating sphere, charge reside over the volume of the surface. So, in this case, the volume density of charge rho equal to the charge divided by volume of the insulating sphere, that is 4/3 pi capital R cube. Its unit is coulomb per meter cube. Okay, understood? Now next. Now, electric field lines. Electric field lines are imaginary line. If a tangent is drawn on this line, this tangent represents the direction of resultant electric field at that point. Okay, and it is the path of a isolated unit positive charge. Okay, so now its properties. Number one, lines of force originates from positive charge and terminates at the negative charge. Okay, look at this. The lines of force terminates at the negative charge or infinity. No problem. The electric lines of force are continuous but not closed. Okay, so number two is the continuous. Okay. Number three, the electric lines of force normal to the surface of the conductor. So look at this. This is the normal to the surface. Okay. No problem. Now number four, there is no electric lines of force within the conductor. The number four, no field lines, no field lines within the conductor. Okay. Now look at this. This is a spherical conducting surface. Now look at this. Now look at this. The four lines are drawn. You have to calculate. You have to identify which one is the electric lines of force. Okay. Now look at this. And now look at this. Okay. Look at this. This is the number one, this is the number two, this is the number three, this is the number four. Which one is the electric lines of force? Now look at this. Look at this. This line is not perpendicular to the conductor, so this is not a lines of force. Look at this. This line within the conductor, so this is not the lines of force. This also not the lines of force. Look at this. This is the lines of force. It enters normally and leaves normally. Okay. So 4 is the electric lines of force. Okay. Understood? Now look at this here. Lines of force originate from this conductor. So this is the positive. Look at this here. Lines of force originates from the conductor. So this is the positively charged. Look at this. This is the lines of force enter into the conductor. So this is the negative charge. Okay. Now next. Two lines of force never intersect each other. If they are intersect at the point of intersection, two tangent can be drawn which represents the two direction of a electric field. This is impossible. Now number 6. Now two lines of force, look at this and this lines of force exert lateral pressure. Okay. The electric lines of force like a rubber cord, they elongate or compressed along the length. Okay. Now the number of lines of force originate from a positive charge or terminates at the negative charge is directly proportional to the magnitude of the charge. Okay. And last point, look at this. The number of lines of force crossing normally on unit area represents the magnitude of electric field. Look at this here. Number of lines of force crossing per unit area more. Here number of lines of force crossing per unit area less. So here electric field more than the electric field at this point. Okay, understood? Now electrical flux. Now electric flux. Electric flux, it is the number of field lines crossing normally on a given surface delta S. Okay. If E be the strength of electric field, then delta phi equal to E into delta S. Okay. So its unit is this is the volt per meter into meter square. So its unit is volt into meter. And dimension, look at this, the dimension of volt is ml squared t minus 2 by at into L. So this dimension is ml cube t minus 3 a minus 1. Okay. And it is a scalar quantity. Now vector definition of flux, the electric flux on a given surface delta S is the dot product of electric field vector in that surface and area vector. Okay. So look at this, delta phi equal to, this is the E vector dot delta S vector, this equal to E delta S cos theta, where theta is the angle between E vector and delta S vector. Suppose this area delta S. So this is the delta S vector. Delta S vector is always normal to the plane. And this is the E vector. And if theta is the angle between them, so look at this, delta phi equal to E delta S cos theta. Look at this, when E vector parallel ds vector, that is E vector is normal to the plane of delta S, then delta phi is equal to, this is the E into delta S. If delta S is perpendicular to the, if delta S vector is perpendicular to the E vector, then look at this, the delta phi, look at the delta phi equal to E into delta S into cos 90 degree equal to 0. Okay. This is the minimum flux, this is the minimum flux, and this is the maximum flux. Okay. Now look at this figure. Okay. This is the closed surface. Look at this, this is the, look at this is the delta S. This is the n vector normal to S. So look at this, the electric flux in this area, this is the E vector delta S vector. Okay, no problem. This is the delta phi. So total flux in the closed surface, this is the phi equal to, this is the surface integral of E vector dot ds vector. Okay. So total flux in a closed surface is the surface integral of electric field vector. The inward flux of this closed surface is taken as negative, and outward flux, look at this, this is the outward flux is taken as positive. If inward flux is phi 1 and outward flux is phi 2, then net flux, this is the phi 2 minus phi 1. Okay, understood? Now Gauss law. The total outward flux over a closed surface is 1 by epsilon naught times the charge enclosed by the closed surface. Look at this, this is the E vector dot ds vector is the total outward flux from a closed surface. This equal to the total charge enclosed by the closed surface. If q be the charge enclosed, then this is the q by epsilon naught. Look at this, suppose this, look at this, suppose outside charge is capital Q, so this charge is only charge enclosed by the Gaussian surface, but electric field responsible for both charge Q and capital Q. Now some common facts about Gauss law. Look at this, the Q of the right hand side is only the charge enclosed by the Gaussian surface, but electric field on the left hand side is responsible both charge inside and outside. Okay. Now number 2, if Q equal to 0, if Q equal to 0, then look at this, this is the E vector dot ds vector equal to 0. So look at this, here E vector may not be 0 because E vector may be parallel to the surface ds. And in this case, look at this, the inward flux is equal to outward flux. And here neat charge, look at this, when here look at this q0, so equal amount of positive and negative charge may present within the surface. Okay, look at this, if q, now number 3, if q greater than 0, so look at this, outward flux phi 2 greater than inward flux. Okay, now Gauss law and Coulomb's law are both applicable for discrete as well as continuous distribution of charge, but use of Gauss law is more advantageous than that of Coulomb's law. Okay, again, the Coulomb's law is applicable only for the stationary charge, but Gauss law is applicable both stationary and moving charge. Okay, so Gauss law is more fundamental than the Coulomb's law. Okay, now the characteristics of Gaussian surface. Look at this, Gaussian surface is the imaginary surface. Number 2, Gaussian surface is the mathematical surface. And number 3, the electric field in the Gaussian surface either parallel or perpendicular to it. Okay, look at this, this is a cube. A charge q is placed at the center. We have to calculate the flux from each surface. Look at this, as q charge is placed at the center of the cube, so flux uniformly distributed over the 6 surface. Now total flux according to Gauss law is the q by epsilon naught. So flux on each surface, this is the q by, this is the 6 epsilon naught. Okay. Now look at this, q charge is placed at the center of a face. What is the flux through this cube? Okay. Now look at this, suppose look at this, this is the face center. So q charge here. Now if another matchbox is placed over it, then the q charge remain within the matchbox. Okay. So look at this, total flux is q epsilon naught. So half of the flux passes through this. So look at this, the flux through this surface, this is the q by 2 epsilon naught. Okay. If q charge is placed at the center of a edge, what will be the flux through the cube? Now look at this, this is the matchbox. Now charge is placed at the center of this edge. Now to keep it to keep in the middle, look at this, another 4 matchbox required. Look at this, here charge becomes top surface. Now look at this, this is the another, this is a, now look at this. So look at this, the 4 matchbox required to keep the charge at the center. So total flux now, this is the q by epsilon naught. So flux on this matchbox, this is the q by 4 epsilon naught. Okay. Now q charge is placed at the vertex of a cube. What is the flux in the cube and flux at the far surface of a cube? Okay. Now look at this, here charge at this point. Okay, now to bring the charge at the center, look at this, this is the 4 matchbox are required. Look at this, so charge here becomes at the center of the top surface. Now to bring the charge at center, another 4 matchbox are required. Okay, look at this, another 4 matchbox are required. So look at this, the total flux is q by epsilon naught. So flux from this cube, is q by 8 epsilon naught. Now look at this, here charge here. So only flux passes through this surface and bottom surface. So 3 surface. So this q by 8 epsilon flux is distributed among 3 surfaces. So flux from a surface, this is the q by 24 epsilon naught. So q by 24 epsilon naught, and flux through the cube, this is the q by 8 epsilon naught. Okay. Example. The electric field components in figure 1.27 are Ex equals to alpha x to the power half, Ey equal to Ez equal to 0, in which alpha equal to 800 Newton per coulomb meter to the power half. Calculate the flux through the cube. B. Charge within the cube. Assume A equal to 1. Now look at this here at this point x equals to a. So here electric field at this point E1 equal to, this is the alpha equals to 800, okay, into this is the x to the power half, so this is the a to the power half, no problem. So flux phi 1 in this surface, this is the E1 into a square. So look at this, this is the 800 into a square into a to the power half. So a to the power, this is the 5 by 2. No problem. Now look at this, at this point, this is the x equals to 2a. Okay. So look at this here, electric flux E2 equals to, this is the 800, this is the 2a to the power half. No problem. So flux phi 2, this is equal to, this is the 800, this is the 2a to the power half into a square. So look at this, the net flux phi equals to outward flux minus inward flux. So phi 2 minus phi 1. So look at this, this is the 800 into a square into, this is the root over, this is the root 2 into, this is the root 2 minus 1 into root 2a. Okay. Now here a equal to 0.1 meter. So look at this, this is the 800 into 0.01 into root over of, this is the 1 by 10 into root 2 minus 1. No problem. So look at this, this is the 8 by root over 10 into, this is the this is the 0.41. Okay. So look at this, this is the net flux. So this equal to q by epsilon naught. So charge within the cube, look at this, q equal to, this is the 8 by root under 10, okay, root under 10 into 0.41 divided by epsilon naught. Okay. Now look at this question number 1.15. Consider a uniform electric field E vector equal to 3 into 10 to the power 3 I cap Newton per coulomb. What is the flux of the field through a square of 10 centimeter on a side whose plane parallel to the YZ plane? Okay. Now look at this plane parallel to the YZ plane. This its area vector. This is the 0.1 whole square into I cap. Okay. So look at this phi equals to, this is the E vector dot A vector. Now E vector equals to, look at this, 3 into 10 to the power 3 I cap. So look at this, this is the 3000 I cap into 0.01 into I cap. So I dot I, look at this, I dot I, this equal to 1. So look at this, this is the 30 voltmeter is the flux. Okay. What is the flux through the same square? If the normal to the plane makes an angle 60 degree with the x-axis. If normal to the plane makes an angle 60 degree, then look at this, the area vector becomes 0.01 into cos 60 degree. So look at this here, this is the 0.01 by 2. So look at this, the 0.005 meter square. Okay. No problem. So flux becomes, look at this, now flux phi 2, now flux phi 2 equal to, this is the 3000 into 0.005. So look at this, this is the 15 voltmeter is the flux. Okay. Now look at this question number 1.16. What is the net flux if the uniform electric field if exercise 1.15 through a cube of side 20 centimeter? Look at this here, inward flux. Now look at this, as field, look at this, as field is uniform. So the inward flux in the cube is equal to outward flux. So net flux in the cube is 0. The careful measurement of the electric field at the surface of a black box indicates that the net outward flux to the surface is 8 into 10 to the power 3 Newton meter square per coulomb. What is the net charge? खूब simple. You know phi equal to, this is the q by epsilon naught. So q equal to epsilon into phi. Now what is epsilon naught? 8 into 8, 5 into 10 to the power minus 12 into, look at this is the net flux, look at this 8 into, this is the this is the 8,000. Okay, so this charge present in the surface. If the net outward flux to the surface of the box was 0, then could you conclude there will be no charge inside the surface? Look at this. If net flux 0, so net charge 0. So equal amount of positive and negative charge may present within the surface. Okay. Now question 1.18. A point charge 10 microcoulomb is at a distance 5 centimeter directly above the center of a square of side 10 centimeter. Shown in figure. Look at this. What is the magnitude of the electric flux through the square? Okay. Now look at this. If a cube is completed, taking this square is the base, the charge will be at the center of the cube. So flux through this surface is the 1/6 of q by epsilon naught. So flux phi equal to 1/6 q by epsilon naught. So look at this, q is the 10 into 10 to the power minus 6. This is the 6 and epsilon is the 8.85 into 10 to the power. This is the minus 12. So look at this. This is the 10 into 10 to the power 6 whole divided by, this is the 6 into 8.85. Okay, this voltmeter. This is almost 2 into 10 to the power 4 voltmeter is the electrical flux. Okay. Now look at this question number 1.19. A point charge 2 microcoulomb is at the center of a cubic Gaussian surface 9 centimeter on edge. What is the net electric flux through the surface? Look at this. Is the q by epsilon. What is q? Q is the 2 into 10 to the power minus 6 and this is the 8.85 into 10 to the power minus 12. Okay. So look at this. This is the 20 into 8.85 into, this is the 10 to the power 6. So, sorry, 10 to the power 5. So look at this. This is the 2.2 into 10 to the power 5 voltmeter is the electrical flux. Okay. Now look at this question number 1.20. A point charge causes the electrical flux minus 1 into 10 to the power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered at the charge. The radius of the Gaussian surface is doubled. No. If the ratio doubled, how much flux would pass through the surface? Flux remains same. Flux does not depends on, this is the area of the surface. It only depends on charge inside the surface. So flux same. What is the value of the point charge? Look at this. This is the q by epsilon naught. This equal to minus 1 into 10 to the power 3. So look at this, q equals to, this is the minus 8.85 into 10 to the power minus 12 into 10 to the power 3. So look at this is the minus 8.85 into 10 to the power minus 9. Okay, understood? Now look at this, the application of Gauss's law. Okay. First of all, the field due to an infinitely long, straight, uniformly charged wire. Okay. Now look at the figure. Now look at this, y dash be a part of a infinitely long straight wire having linear density of charge lambda. This is number 1 point. Number 2 point, the P is a point at a distance smaller from y dash where we have to calculate the intensity E. Okay, number 2 point. Number 3, Gaussian surface. A cylindrical Gaussian surface of length L and radius R is drawn having y dash as its axis. So on the curved surface, look at this, E vector is parallel to ds vector. Okay, and on the flat surfaces, E vector perpendicular to ds vector. As E vector perpendicular ds vector, so flux on the flat surface is 0. But flux on the curved surfaces, look at this. This is the E vector dot ds vector. This equals to, look at this. This is the E ds cos 0 degree. So this is the E ds. What is the ds? The area of the curved Gaussian surface. So this is the E into 2 pi RL is the total flux through the Gaussian surface. Okay. Now applying Gauss law. Chart number point. Now 4. Now point number 4. Look at this, applying Gauss law. Look at this, E vector dot ds vector. This equal to charge enclosed by the Gaussian surface. As length of the Gaussian surface is L, so charge enclosed by it is the lambda L. So this by epsilon naught equal to E vector dot ds vector surface integral. So look at this. So look at this, E vector dot ds vector surface integral, this equals to E into 2 pi RL equals to lambda L by epsilon naught. So look at this, E equal to, this is the lambda by 2 pi epsilon naught R. Okay, no problem. If a graph is plotted between E and R, look at this graph is rectangular hyperbola. That is E proportionate 1 by R. Okay, understood. And in this direction, this is the E. Okay, now a numerical related to this. Now numerical 1.23. Okay, an infinite line charge produces a field of 9 into 10 to the power 4 Newton per Coulomb at a distance of 2 centimeter. Calculate the linear density of charge. You know, electric field due to infinitely long straight conductor. This is the lambda by 2 pi epsilon naught into R. Okay. What is lambda? Look at this. Lambda is this. What is R? Look at this. R is this. So now lambda equal to, this is the 4 pi epsilon naught R by RE divided by 2. Okay, now look at this, the value of this is the 1 by 9 into 10 to the power 9. Value of R, look at this is the 2 centimeter. So look at this is the 2 into 10 to the power minus 2. What is E? Look at this is the 9 into 10 to the power 4. And look at this is the 2, so this is the 2. Now this cancel out. Okay, now this 9 and this 9 cancel out. So look at this is the 10 to the power 4 and 10 to the power minus 2. So look at this is the 10 to the power 2. So 10 to the power minus 7. This is the linear density of charge. So lambda equals to, this is the 10 to the power minus 7. This is the Coulomb per meter. Okay, next. Field due to a uniformly charged infinite plane sheet. Okay. Now look at this. This is the infinitely plane sheet in the YZ plane. Look at this. This is the Z axis. Okay. Its surface density of charge sigma. Number 2 point, we have to calculate the E near a point. Number 3, a cuboidal Gaussian surface is drawn having, look at this surface, and this surface is parallel to the C. Okay, so at this surface, E vector parallel to ds vector. So flux in these two surface, this is the EA plus EA, and flux on other surfaces is 0. Now number 4, the charge enclosed by the Gaussian surface, look at this is the A into sigma. Now applying Gauss law, look at this is the number 5, this is the E vector dot ds vector, this equal to charge enclosed, this is the sigma A divided by, this is the sigma A by, this is the sigma A by epsilon naught. So look at this is the E plus E, 2E, this is the EA plus EA, so this is the 2EA, this equal to sigma A by epsilon naught. So E equal to, so look at this, so E equal to, this is the sigma by 2 epsilon naught. Okay, no problem. Now look at this is a plate, here surface density of charge on this surface, this is the sigma, and surface density of charge on this surface is also sigma. We have to calculate intensity at the point P1 within the plate P2, and this is the pitch. Okay, now look at this intensity at P1 due to this charge. Look at now intensity at this point due to this charge, this is the sigma by 2 epsilon, and intensity discharge, this is the sigma by 2 epsilon. Okay, so look at this, the total charge is sigma by epsilon naught. Okay, now at the point P, look at this, due to this charge it is directed away from it, due to this charge it directed away from it. So look at this, these two field cancel out. Okay, now at P3, look at this, due to this charge it is directed in this direction, due to this charge it is directed in this direction. So look at this, here intensity becomes sigma by epsilon naught. Okay, now a numerical related to it. Now look at this question number 1.24. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite sign and magnitude 17.0 into 10 to the power minus 2 coulomb per meter square. What is E in the outer region of the first plate, outer region in the second plate, and between the plates? Okay, now this is a plate, and look at this, this is a plate. Okay, look at this, look at this, here surface density of charge, this is the positive and sigma. Look at this, here surface density of charge, this is the negative and sigma, minus sigma. Now we have to calculate intensity at this point. Look at this, due to these positive charges, the intensity directed along this direction, and due to these negative charges, intensity directed this direction. So net intensity is equal to 0. In the same way, intensity at this point due to these negative charges directed along this direction, these positive charges directed along this direction, so here E also 0. Now between the plates, look at this, due to positive charge it is away from the charge, due to negative charge towards the charge. So within the plates, this is the sigma, this is the E equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So this is the sigma by epsilon. What is the value of sigma? Look at this, sigma is this. So look at this, this is the 17.0 into 10 to the power minus 2. What is epsilon naught? Look at this, epsilon naught is the, this is the 8.85 into 10 to the power 9. Okay, this is the 22. So look at this and this is the 2. Okay, so look at this is the 2 into 10 to the power, this is the minus 11. So 2 into 10 to the power minus 11 volt per meter is the electric field within the conductors. Okay. Now, field due to a uniformly charged thin spherical shell, okay, or conducting sphere, because both have surface density of charge. Okay. Now look at this. Now number point 1. Look at this. This is a spherical shell having charge q. So its surface density of charge sigma equals to q divided by 4 pi r square. Number 2. Now P is a point at a distance r where electric field is obtained. Number 3. Look at this. A spherical Gaussian surface of radius small r passes through the point P is drawn concentric with the spherical shell or conducting sphere. No problem. So look at this. So this is the Gaussian surface. No problem. Now number 4. On the Gaussian surface, E vector parallel to ds vector. Look at this here. E is the radially outward and ds is also radially outward. Now 5. The total flux, this is the E vector dot ds vector. This equal to, this is the E ds cos 0 degree. This is the surface integral. So this is the E into 4 pi small r square. Now charge enclosed by this Gaussian surface Q. So look at this E into 4 pi small r square. This is the Q by epsilon naught. So E equal to this is the Q divided by 4 pi epsilon naught r square. So E proportionate 1 by r square. Okay. So look at this. The intensity is inversely proportional to distance from the center. So we may consider the whole charge of the spherical shell or Gaussian surface is concentrated at its center. Okay. Now electric intensity on the surface. Here smaller equal to capital R, and charge enclosed by the Gaussian surface is also Q, and this equals to 4 pi r square sigma. Okay. Now look at this. Using this relation we can get E into this is the 4 pi r square 4 pi r square equal to this is the Q by epsilon naught. So look at this E into 4 pi r square. This is the 4 pi r square sigma by epsilon naught. Look at this. This is the 4 pi r square. This is the 4 pi r square. So E equals to sigma by epsilon naught. Therefore, electric field on the surface of the conductor or spherical shell does not depends on radius of it. It is constant. This is the sigma by epsilon naught. This statement is known as Coulomb's theorem. So Coulomb's theorem equal to E equal to sigma by epsilon naught. As field is radially outward, so E vector becomes this is the sigma by epsilon naught n cap, where n cap is the radially outward unit vector. Okay, no problem. Now intensity within the spherical shell. Look at this here, smaller less than capital R. So charge enclosed equal to 0. So using this relation, E into this is the 4 pi r square equal to 0 by epsilon naught. So E equal to 0. Therefore, electric field within the conducting sphere or spherical shell is 0. Now, now look at this question number 1.21. A conducting sphere of radius 10 centimeter has an unknown charge. If the electric field 20 centimeter from the center of the sphere is 1.5 into 10 to the power 3 Newton per Coulomb and points radially inward, what is the net charge on the sphere? As the field is radially inward, so charge is the negative charge. Now field E equal to this is the Q divided by 4 pi epsilon naught r square. So what is E? Look at this. E is the this is the now E is the look at this 1.5 into 10 to the power 3. Okay, and this equals to 9 into 10 to the power 9, and this is the Q, and this is the 0.2 whole square. So Q equal to look at this is the 0.04 into this is the 1.5 into 10 to the power this is the 3 whole divided by 9 into 10 to the power 9. So look at this is the 60. So 60 by 9 into 10 to the power minus 9. So look at this is the 6.6 into 10 to the power minus 9 Coulomb is the charge within it, and this charge is the negative charge. So Q is the minus 6.6 into 10 to the power minus 9 Coulomb. Okay. Now look at this 1.29. A hollow charge conductor has a tiny hole cut out into its surface. Okay, look at this. This is the conducting. Now look at this is the charge conductor. A tiny hole. Look at this. This is the tiny hole. Okay, is cut out so that the electric field in the hole is sigma by 2 epsilon naught n cap. Okay, where n is the unit vector outward normal direction and sigma is the surface density of charge. Now consider 2 points. Suppose this is the P1 and suppose this is the P2. Okay, no problem. Look at this, the electric field due to this tiny hole, this is the E1, and electric field due to rest of the conductor, this is the E2. So outside the spherical shell, the electric field, look at this is the E1 vector plus E2 vector, this equal to sigma by epsilon naught n cap. Now inside, look at this, the inside the cavity, the electric field is 0. Now look at this within the cavity. Suppose look at this is the E1 vector minus E2 vector, this equal to 0. So look at this is the E1 vector equal to this is the E2 vector. No problem. So now put the value of E2 in this equation. Look at this, we get E1 vector plus E1 vector, this equal to sigma by epsilon naught n cap. So look at this is the E1 vector equal to sigma by 2 epsilon naught n cap. Okay. So electric field in the cavity is sigma by 2. Electric field in the hole is sigma by 2 epsilon. Okay. Many thanks for watching this video. This video will be extremely helpful in CBSE, 10+2, main, NEET and advanced. Like, share, comment on this, and to get the best score in CBSE, NEET, main and advanced, don't forget to subscribe my channel. Okay.